The type of reaction that we're working on now is the double replacement reaction. The double replacement reaction is essentially a reaction in which the positive ions in two compounds trade partners or swap positions. In the double replacement, we're going to take the positive ion in our two compounds and trade places. So in this case, our A and our X will switch their partners and match with the negative ions. The resulting compounds that we form as we trade partners would be the positive ion X is now matched with the negative ion B, and the positive ion A has now traded and is matched with the negative ion Y to form our new compounds. Possible outcomes are we can make a solid precipitate, or we could have a product that's going to be a gas. The product combination could form something that's a molecule, which is essentially making something that is a non-electrolyte. And it's possible that we could have it where it just does absolutely nothing and we have no reaction taking place. Let's examine each possible outcome, starting with forming a solid precipitate. Our first step is we're going to trade positive ions. So we're going to swap our Pb2 plus ion with our K1 plus ion. A suggestion is write the ions separate from each other with their charges so that we can get the correct formula when we put together the new compound. K1 plus and NO3 minus means we need one of each piece, so we have KNO3 plus, and then our lead, because it's plus 2, combined with the iodide, which is minus 1, it's going to be PbI2. Once writing the formulas, now let's balance the equation. Now balance the equation by putting a 2 with the Ki and also a 2 with the KNO3. Next, we need to identify with our products if either of the products make something that is insoluble. Something that's insoluble would be a product that is a solid or is a formation of a precipitate. Looking at the solubility rules chart, we can see that all nitrates are soluble. That means KNO3 is going to be a product that is aqueous or still dissolved. Also, all compounds containing a 1A element, such as potassium, are also soluble. So potassium nitrate is soluble and the product will be aqueous. On the other hand, lead iodide. Looking at the solubility rules, all iodides are soluble except for silver, mercury, and lead. Lead iodide is insoluble. That means this will make a solid precipitate product. Our next step is to write what's referred to as the overall ionic equation. This is taking materials that are aqueous and strong electrolytes and writing them as they actually exist in solution, which means the ions exist separate from one another as aqueous ions. The overall ionic equation would look like this. The lead nitrate exists as separate lead and nitrate ions in solution. The potassium iodide exists as separate potassium and iodide ions. The potassium nitrate aqueous is separate potassium nitrate ions, but the lead iodide, because it's a solid, remains intact with the ions connected, forming the solid precipitate. The third step is to reduce this to net ionic form. To reduce to net ionic form, we want to identify anything that remains unchanged chemically on the reactant and product side. For example, we have the nitrate ions that remain unchanged, that are aqueous, and we have potassium ions that remain unchanged and aqueous. These ions can be eliminated from the equation because they're doing nothing chemically in the chemical process. The only materials left are the Pb2 plus aqueous plus the 2I minus aqueous ions give us our PbI2 precipitate solid, and this would be our net ionic equation. This would be the expectation for reactions that we can identify ions that participate, keep those ions, identify ions that do nothing, eliminate those, and write what's known as a net ionic equation. Next, let's examine formation of a gas in a double replacement reaction. There's only 4 possible products in double replacement reactions, that can create a gaseous product. H2S, H2CO3, H2SO3, NH4OH. The first, H2S, is a gas immediately upon formation. The other three decompose to form a gas. The carbonic acid will decompose to make carbon dioxide gas and water. The sulfurous acid decomposes to make SO2 gas and water, and ammonium hydroxide decomposes to make ammonia gas and water. This would be an example double replacement that can make a gaseous product. We have our two reactants, sodium carbonate and hydrochloric acid. The first order of business is to swap the positive ions to identify our new products. The suggestion again is write the products as ions first to make sure we get the formulas correct when we combine the ions with their new partners. The products we make in this reaction are H2CO3, carbonic acid, and sodium chloride. Let's quickly make sure we have the equation balanced before moving forward. The equation can be balanced by putting a 2 by the HCl and a 2 also by the NaCl. What we need to recognize now is the H2CO3 product is going to decompose into CO2 gas plus H2O. And this would be the proper way to represent the products in this reaction. So we're going to take out the H2CO3 and rewrite it as CO2 gas plus H2O. The other product in this reaction, sodium chloride, has sodium in it, which is an alkali metal, and all alkali metal or column 1A elements in a compound are soluble, so the sodium chloride we can designate as aqueous, meaning it will be dissolved in water. Our next step is to write the equation in overall ionic form. Anything aqueous that dissociates, we're going to separate into ions. So our sodium we write as sodium ions and carbonate ions. Now hydrochloric acid, because it's a strong acid, means that it dissociates 100%. That's what strong acids do, so we can write this separate as H plus aqueous ions and Cl minus aqueous ions. Our CO2 is a gaseous molecule, H2O is a liquid molecule, and our sodium ions are still aqueous and the chloride ions are still aqueous. Our third step is to now identify our spectator ions and eliminate the spectator ions from the equation to reduce to net ionic form. The ions that do nothing in the reaction and remain unchanged are our aqueous sodium ions and our aqueous chloride ions. We'll eliminate these from the equation to simplify and reduce to net ionic form. This would now be the net ionic equation for this reaction. It's carbonate ions reacting with H plus ions to make carbon dioxide and water, a gaseous product for a double replacement reaction. Another outcome is we could make a molecule. This would be forming something that is an aqueous non-electrolyte or near non-electrolyte, or a molecule such as water. The only two things that'll be molecular products is if when we do the double replacement, we make a new product, a new item that's a weak acid, or something that is a water molecule. Our first step again is to take our reactants and find out our products by switching the positive ions. So we're going to swap our Na plus and H plus ions to get our new products. Again, the suggestion is write the ions separate first to make sure we write the formulas correctly based on the charges on the positive and negative ion. This gives us our product molecules of HClO2 and also sodium chloride. Sodium chloride, because sodium is an alkali metal, this will be soluble. We can write this as aqueous. The HClO2 we can identify as a weak acid molecule. What this means when something is a weak acid is that this will remain as an aqueous non-electrolyte molecule that's dissolved in water. Our next step remains write the overall ionic equation, which we then use to reduce to net ionic form. This is our overall ionic equation, separating aqueous things that dissolve and are strong electrolytes into their separate ions, such as sodium ions and chloride ions. HCl, because it's a strong acid, the ions exist separate from each other as H plus and Cl minus. The HClO2 product, though, because this is a weak acid, these materials remain connected together as an aqueous non-electrolyte molecule that's in solution. The sodium ions and chloride ions are separate in solution. We now want to identify our spectator ions, eliminate the spectators, and reduce to net ionic form. Our spectator ions on the aqueous sodium ions, aqueous chloride ions, they can be eliminated. This leaves us with our net ionic equation of chloride ions, aqueous, plus H plus aqueous ions, gives us our weak acid molecule, HClO2. This would be an example of a double replacement reaction that forms a molecule as a product.